Welcome to section 4.5. In this section, we're going to be thinking about integration by substitution. So you guys have some really useful tools like that power rule to help you integrate, but sometimes you will run into problems that you really don't have the tools for. For some of those functions or those integration problems, you'll need to use this thing called U substitution. So our objectives for today, we want to recognize the pattern that will lead us to use U substitution to find an indefinite integral. We're going to use this change of variables. That's where the U comes from in U substitution. And then right now, these are all talking about indefinite, indefinite, indefinite. We will also be applying this to some definite integrals and figure out, how can I solve and get just a number for a definite integral, all right? So here's our definition of U substitution. We're going to be practicing this technique, and it's honestly kind of similar to the chain rule in a way. Okay, so anti-differentiation of a composite function. Let G be a function whose range is in the interval I. Let F be a function that's continuous. If G is differentiable and if F is an antiderivative, so differentiable there, right, we've kind of talked about this a little bit. Is it able to, or am I able to find an antiderivative? It's related to continuity, but it's am I able to find an antiderivative? So you have this outside function over here. And then G is kind of your inside function. So G is your inside function. And then you should also see the derivative of your inside function. So this is the pattern that we're going to start to kind of recognize. You'll have some kind of composite function, a function within a function, and then that's multiplied by the derivative of that inside function. When that happens, then I can say, okay, let me find the antiderivative of that outside function, leaving that inside function alone, and add C. So just a little reminder, our chain rule, the way that we would apply it, we would say, okay, f of x is 3x plus 2 to the third. My derivative of that would be pull down that 3, right, from the exponent over here, leave that inside function alone, subtract 1, and then multiply by the derivative of that inside function. So we would end up with 9, 3x plus 2 squared. So we want to be on a lookout for something that looks kind of like this. We're going to do kind of a reverse process. But with the g of x, the f of x, it gets really confusing. So we are going to set u equal to g of x. We're going to be solving for du. And we are going to be doing lots of substitution. We want to make sure that our variables match. So if I'm using u as my variable, I want to make sure that somehow I can also exchange the dx for something with du in it. Okay, then we will end up with a function that's way easier for us to actually anti-differentiate. So let's try this out with example 1 over here. Here's how we want to recognize this. So right now, we don't really have a good way to do this. I guess you could FOIL out this first part, then multiply by 2x. That honestly seems kind of long and complicated. I don't love that option. But what we're noticing here is that this right here is kind of a composite function. It's a function within a function. It's f of g of x. Okay, so that g of x is that inside part, x squared plus 1. G prime of x, what would that be? What's my derivative of that function? Oh, that's just 2x. That's exactly what I'm seeing right over here. This is my derivative of that inside function. So f of g of x is f of x squared plus 1. I can see that my f function is just something squared. That is that x squared plus 1 squared. Okay, so what we want to do here is I would like to, kind of scrolling back up here, I want to find the antiderivative of that outside function. So if I just have something squared, well, my antiderivative would be that thing raised to the third and then divided by 3 plus c. Instead of just having x or something, I have this whole inside function, x squared plus 1. You can either leave your answer like that, or you can write it by pulling out the 1/3 all the way out in front. Those are both equivalent forms. Both of these would be accepted answers for something like this, okay? And you can always, 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 if you want to check your answer, take the derivative. Take or find the derivative. And you should get back to whatever you see inside your integrand, basically. All right, let's keep going with this. Let's try another one. We'll try one with trig. Okay, find 5 cos 5x. So if it was just 5 cosine x, you guys could do this, but we have yet to deal with another number inside the trig function. So this part right here, that is our f of g of x. My g of x function, I'm going to say is 5x. So what would g prime of x be? That's just 5. That's exactly what I'm seeing over here, g prime of x. So see this pattern? It's a composite function times the derivative of the inside function. That's the pattern you're looking for. When you see that pattern, then you can just leave that inside function, that 5x alone, and just integrate that outside function. So what's the integral of cosine? It should be sine. I'm going to leave that inside function alone, 5x plus c. Okay, so that is our answer for this one right here. Again, to check it, if you were to differentiate this, dx sine of 5x, well, that would be take the derivative of the outside function, cosine 5x, and then multiply by the inside derivative, 5. Boom, I'm right back to where I started. Okay, so that's kind of the pattern recognition that we are working on right now. Sometimes we need to do it slightly differently. Sometimes I need to multiply or divide by a constant or rearrange something. So we're going to see that in this next example, example 3. So for this one, again, here is kind of my composite function. So I'm going to say that g of x is x squared plus 1. My derivative of that, okay, this is very similar to what we just did. My derivative of that is 2x, but I only see x, not 2x, okay? Because I just see x, I can think about multiplying and dividing by 2. So I'm going to rewrite this as follows. X squared plus 1 squared, all right, that's what I see right here. That's this portion. And then I'm going to multiply and divide by 2. 1/2 times 2x. Okay, see how I multiplied and divided by 2? 2 over 2. I just split them up a little bit. It's the same thing as just multiplying by 1. And then I have dx. Okay, so now I see that g prime of x. Okay, so I have that f of g of x, and I have g prime of x, and I just have this swanky little constant, but you guys know that I'm allowed to pull out a constant, right? So this constant right here, I can pull outside of the integral. So I have 1/2, and then we are finding the antiderivative, so capital F of g of x. So that's going to be x squared plus 1 to the third divided by 3. Because it's indefinite, always plus c. And then I'm going to simplify that a little bit by combining the 2 and the 3. So we have 1/6 x squared plus 1 to the third plus c. And that is our answer to this one. So again, sometimes I just need to rewrite this by multiplying and dividing by a constant. 1/2 times 2, that's the same thing as multiplying by just 1, right? And that was helpful. We use that to our advantage to rearrange this. Okay, I think changing your variables makes this way easier. So instead of trying to find this f of g of x, g prime, blah, 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 I am literally going to set u equal to that g of x function. I'm going to replace it entirely. I'm also going to have to figure out what my derivative of u is. We're going to also have to replace dx with something involving du. And I'm going to use u as my new variable instead of x. You'll see that this way is a little bit easier when we do this first example, all right? Okay, find the square root of 2x minus 1. Right now, I mean, you guys could rewrite that as 2x minus 1 to the 1/2, but I haven't really taught you how to do it, how to do something like that when you have a whole function inside. So I do have to use u substitution. I'm going to set u equal to this inside function, this 2x minus 1. What I want to do now is I want to integrate this. Another way, we've been using g prime, but remember another way, and by integrate, yikes, I mean differentiate. We've been using g prime of x, but remember another way to notate differentiation is du dx. So I'm differentiating u with respect to x. My derivative here would just be 2. I want to rearrange this to get du by itself. So I'm going to multiply both sides by dx. Du is going to equal 2 dx. And then I want to keep going. I want to get dx by itself. Dx is going to equal du over 2. So I need to change variables here, or because I'm changing variables, I need to change dx somehow to du. because I'm changing the variable with respect to which I'm integrating. So changing which variable I'm integrating. Instead of integrating x, changing which variable I'm integrating. Instead of integrating x, I am now integrating u. Okay, so this whole thing now I'm going to rewrite as the integral of the square root of u, and then I'm going to replace this dx with du over 2. Well, that over 2, that's the same as 1/2, right? So I'm going to, again, pull out a constant, 1/2 integral of square root of u du. Guys, you know how to find the integral of the square root of u, right? That's u to the 1/2. So we have that 1/2 out in front, u to the 1/2, I'm going to add 1, so 3 over 2. I'm going to divide this whole thing by 3 over 2. I'm going to add c. Let's simplify this a little bit. I would have 1/2 times 2 over 3 u to the 3 over 2 plus c. Those 2's would cancel, and I'd be left with 1/3 u to the 3 over 2 plus c. If you wanted to rewrite that even nicer, you could say 1 over 3 square root of u to the 3rd. Your final step, replace u with your original function. So I have 1/3 square root of 2x minus 1 cubed plus c. And that is your final answer. Folks, you will see some problems that have the fractional exponent left in them. In this section, we won't always convert it back, but it is still good practice to convert it back when you can. Guys, you're halfway through. Let's keep going with this. Somehow we jumped from example 4 to example 6. Whoops. Okay, for this one, what should we set u equal to? So we want to be careful here. At some point, I know that I'm going to find the derivative of u, or, you can think back to the beginning, find the derivative of g of x. So should I set u equal to cosine 3x? Should I set it equal to sine 3x? Should I set it equal to something squared? We have a lot of options here, okay? I am going to set u equal to sine 3x. Remember, if you ever see something like this, it's the same thing as sine 3x squared, right? So sine 3x is really our inside function for this problem, all right? That's why I set this equal to sine 3x. Find your inside function. Now I'm going to differentiate this. Du over dx, and again, we know that we're going to end up multiplying by dx, so du equals, I need to chain rule this, so this is going to be cosine 3x, but then times 3 dx. All right, we're going to rearrange this to solve for dx. That's going to be du over 3 cosine 3x. Okay, let's do our substitution here. I'm substituting u for sine 3x, so that's going to give me u squared. And I still have this cos 3x over here, but then I'm also replacing the dx with du over 3 cos 3x, okay? Oh, this is lovely. The cos 3x, that cancels out. I have that 3 in my denominator. That's a constant, though, so I can go ahead and pull that out front. So what I'm left with is 1/3 the integral of u squared du, and you guys can integrate that. 1/3 u to the 3rd over 3 plus c. That's 1/9 u to the 3rd plus c. Make sure to always replace your u, 1 over 9. And then u we said was sine 3x. I want to cube that plus c. But guys, remember, for trig functions, we don't tend to write it like this. We want to put that little cube right next to the sine. So 1/9 sine cubed 3x plus c. And that is the answer we're looking for. Again, when in doubt, check your answer. Differentiate this, find the derivative, and make sure it matches your integrand, your original integrand. And this is just to check. Alrighty, let's keep going. So again, I like to show you guys lists. Some of you might be list people like me. These are your guidelines. You're choosing a substitution, and sometimes trial and error. Sometimes you have to try something and see if it'll work and make sense. And if it doesn't, go back and try something else. We want to try to choose this inner function, the inner part. Okay, so something maybe raised to a power. Then we're going to compute this. So this, I'm basically, finding my derivative, finding an expression for du. I'm going to rewrite, I'm replacing that function with u. I'm going to integrate, find the resulting integral. At the end, I'm replacing u back with the original function to obtain something in terms of x, and then I'm checking my answers by differentiating. So that is your step-by-step process here. I'm going to show you 5 different examples on this next page. Again, pattern recognition, just making sure, hey, what would you guys choose as u? What would make sense here, okay? So here are these examples. So for A, what should we say u is equal to for this one? Well, I think this right here should probably be u. So this whole thing would get rewritten as, the 3x minus 1 to the 4th, that's u. And the 3 dx, that's du, right? If I were to find the derivative of 3x minus 1, it would just be 3. So really what we're left with here is I have u to the 4th du. When you, when you integrate that, you would get u to the 5th over 5 plus c. Your step here is to replace, so 3x minus 1 to the 5th over 5 plus c. There you go, boom, okay? For this next one, which one of these should I set equal to u? Which one of the, like if I were to find the derivative of this, what would that be? Well, that'd just be 2. But if I were to find the derivative of this, what would that be? Oh, that'd be 2x plus 1. Beautiful. So what we see here is that this is just going to be u to the power of 1. And then du is going to be this part over here, dx, right? So this whole thing just turns into u du. I know that is just u squared over 2 plus c, or x squared plus x squared over 2 plus c. There's your answer right there. So pattern recognition. All right, for this next one, what should we set equal to u? Hopefully you said this inside function. So I'm going to rearrange this a little bit. X to the 3rd minus 2 to the 1/2, right? That's the same thing as a square root. I'm just rearranging over here. I have 3x squared times dx. This whole first part would just be u to the 1/2. This part is du. So I know that integrating this would give me u to the 3 over 2, 2/3 u to the 3 over 2. And I want to replace that u with our x cubed minus 2 plus c. That's the answer you're looking for. Again, you could rewrite this fraction with a radical symbol. All right, for this next one, what should we set our u equal to? Hopefully you said this inside function down here. So I'm going to rewrite this as 1 minus 2x squared to the negative 2, right, because it's in our denominator, times negative 4x dx. So this part I would rewrite as u to the negative 2. This part over here, that would be du, right? If I were to find the derivative of this, it would just be negative 4x. To integrate that, I'm going to add 1 to that numerator. So I'm going to have u to the negative 1 divided by negative 1 plus c. I could rewrite that as just negative 1 over u plus c. So we should end up with negative 1 over, replace it, 1 minus 2x squared plus c. That's what you're looking for. See if you can try out this last one. So for this one, the signs get a little funky here. Our inside function is officially cosine for this one. So I want to think in terms of some negatives over here. So I'm going to rewrite it like this. So cosine x squared, that I would replace with, u squared. And then I have sine x dx. Here's what we're going to do. I know the derivative of cosine is negative. So we said when we were missing like a constant, you could multiply and divide by that same constant. What I'm going to do here is I'm going to multiply by negative 1 twice. So negative, negative. That is the equivalent, right? If I have a negative times a negative, it's back to the positive. Now, though, that lets this whole part be equal to du. So I just have this negative out front. That's okay. That's allowed, right? Negative times negative equals a positive. So this is going to become negative cosine x cubed over 3 plus c. And I can rewrite that a little nicer. Cosine cubed x over 3 plus c. That's what we're looking for. All right, so I know I just ran through those. Again, take as much time as you need. But the whole point of this is just try to do some pattern recognition here. What should you set equal to u? How can you shorthand some of this? We only have a few more people. Good job. Here is what we would do with definite integrals. So with definite integrals, they start you out with a and b, but when you change your variables, sometimes it's really helpful to also change your upper and lower boundaries. So to do that, you are going to plug in a and b for x to solve for new limits of integration. And I will show you exactly what I mean by that with our example over here. So if the function u equals g of x has a continuous derivative on the closed interval, then I can change that. I can also change my limits, and then I'm just plugging those in for u instead of having to replace u with your original function and plug in things for x. Okay, so again, easiest way to understand this is let's do an example. So here's our example. What should we set u equal to here? Well, an inside function here would be x squared plus 1. What is the derivative of that function? Well, it would be 2x dx. All right, I can rearrange that and say x is equal to du over 2x. I like that. For your lower limit, I'm going to plug in 0 every time I see x. So 0 squared plus 1, that's going to be 1. And then for my upper limit, I'm going to do the same, but with b, u equals 1 squared plus 1 or 2. Okay, so I can rewrite this whole thing with new limits of integration. The new lower is 1, the new upper is 2. This I'm going to replace u cubed. And then I still have that little pesky x, but that's going to go away in a second. I'm replacing dx with du over 2x. Those x's now cancel out. I do still have that 2 in the denominator, but I can just pull that 1/2 out front as a constant. I have 1, 2, u cubed du. And you guys can integrate that. I would have u to the 4th over 4. I'd like to evaluate that at 2 and 1. So no more c's because now we're jumping to definite integration. Those c's would cancel. I have 1/2. If you were to plug in 2, you would get 2 to the 4th or 16 over 4. If you were to plug in 1, you'd get 1/4. That leaves us with 1/2 times 15 over 4, which equals 15 over 8. And that is the answer that we're looking for here. So the change of variables is pretty nice because now you can just plug in for u. If you change these to, limits of integration, you're just plugging in for u. Otherwise, you'd have to replace u with your original function and use your original limits. And that just gets really complicated. Okay, so just make sure if you're doing a definite integral, change those limits of integration. It makes it so much easier. All right, folks, you have a couple of worksheets. You'll be using processes very similar to these. I want you to try them out, see how well you can do. This is an example. This is number 1 on that u sub with indefinite. So just taking a peek here, what would you set equal to u, just to kind of get you started? I would probably want to set that inside function here, x to the 4th minus 2 equal to u. And then keep going with this. What would du equal? Okay, 4x cubed dx. See what you can do. See what you can replace. Because it's indefinite, you're going to have to do plus c for all of those ones. On that second worksheet that I'm giving you, it is definite integration. So for this one, for some of them, they're telling you what u should equal, which is super nice. From there, you can figure out what du would be. Okay, 4x dx. For these ones, you should be able to cancel some stuff out nicely, but then also make sure that you are plugging in your upper and lower limit. So your new lower limit of integration would be u equals 2 times negative 3 squared plus 3. So that would be what? 2 times 9 plus 3, 18 plus 3, 21. You can check me on that. Please check me on that. Your upper limit, instead of 0, you're going to plug 0 in for x. So you get 2, 0 squared plus 3. That's just going to be 3. Okay. So this one's kind of funky. It's actually kind of changing them quite a lot. But again, to find your new lower and upper limit, you are just plugging in your original a and b in for x in your u equation. Okay. So see what you guys can do with those. Mark any that you have issues with. The keys are in the subplan. You've probably already seen them. Good luck. I'll see you in the next video.